morning, everyone. I trust you're all doing well. Can I please just ask for an indication on whether you can see my screen, either by typing in chat or just giving me a thumbs up? Thank you. I see a thumbs up there. Okay, so welcome to today's GOC session, technical session. Today's session will be on I/O mapping and memory. So today we will be covering the different types of memory that the GOC has, as well as how the addressing works and how the I/O is mapped. So to start off, we'll start with the memory. So during the development phase of any type of project, it's always important to know what type of memory your PLC has and what the functionalities thereof is. So for the GOC, as you can see in this illustration, we have RAM memory, which holds your PLC variable data, your flash memory, which holds the application program code and source code, and your FRAM memory, which holds your retained data and your settings. As you can see, each type of memory has its purpose, and each of these memory types can also be further subdivided according to functions. To start off, we'll start with the RAM memory. The first subdivision would be your input process image. These are your input, or is your input data of your GOC, which can further be divided into your main unit and extension modules, and your communication protocol interface. The second subdivision of your RAM memory is the output process image, which is the output data of your GOC. This can also be divided into your main unit extension modules, as well as your communication protocol interface, similarly to the input process image. The third subdivision is the marker memory, and the fourth is the data memory. These two aren't further subdivided, but an important note for these two memory types, they are, or part of these memories can also be declared as retentive, meaning a part of this memory can also be located in the FRAM. The input process image, as mentioned previously, stores the input data of the GOC, which includes your main unit, extension modules, and your communication protocol input data. The main unit and extension modules has a size of 32 bytes, with the addressing being in input byte 0 to input byte 31. So just as a note, we will be going through the addressing a bit later and the formatting thereof. So if this doesn't quite make sense for now, it will be explained a bit later on. Communication protocol has a size of 2016 bytes, with the range for addressing ranging from input byte 32 to input byte 2047. None of the input process image memory can be retained. The output process image memory, as mentioned, is the output data of the GOC, which identically to the input process image memory, stores both your output data of the main unit and extension module, as well as your communication protocols. The main unit and extension module's size is also 32 bytes, with the addressing being from output byte 0 to apologies, that is incorrect, output byte 31. The communication protocol interface also has a size of 2016 bytes, which ranges from your output byte 32 to output byte 2047. None of this memory for the output process image is retainable. The next is the marker memory. So the marker memory is used to store intermediate results. So during your processing, whether you want to work out a value or something of the sort, and it doesn't necessarily get outputted or is not an input, you'd use your marker memory. The range for the marker memory is from marker memory byte 0 to marker memory byte 32,767. In this memory, there's a designated range which can be retained, being the marker memory byte 31,744 to marker memory byte 32,767. The last memory type for the RAM is the data memory, which stores both your intermediate results as well as function block instance data. As opposed to the other variable memory types, this memory type does not have addressing as it uses symbolic names. This is possible because Codesys assigns the addresses to these variables automatically during compilation, which means that this address is not fixed and can and will change over multiple compilations. 3,000 bytes of this memory is designated or can be designated by the user as retentive. We now move on to the flash memory of the GOC. The flash memory is used to store the application program, which is well, the flash memory is also non-volatile memory, meaning that your program is not lost when the power goes out. The application program can be further subdivided into your application program code and your source code. The size of the flash memory is 64 megabytes. So just to point out this illustration, as we mentioned, so we have the application program code, application data, and application program source code. I will be explaining each of these in a moment. So the application program memory. This memory within the flash memory stores the application program code. The program code or your boot project is the program that the GOC43 processor executes. So that is the logic that the PLC will execute. The maximum size for this boot project or source application program code is 8 megabytes. So that is 8 of the 64 overall flash memory. This application program code is irretrievable. Therefore, when you try and read it from your GOC, it can't be used to download to another GOC, as it is not a complete project file. Your application data memory stores the visualization, fonts, images, text lists, and other system files, which are present in your overall project. This is downloaded to the GOC when you download the application program code, but the size or these files are not included within the 8 megabyte maximum size of your application program code. So this generally falls under the 64 megabytes. These files or set visualization fonts, images, and such only need to be downloaded to your flash memory once. Once you have downloaded once, it is not downloaded again. Only application data that has been added or changed is downloaded to the GOC again. Another important note is that, yes, the application data is not downloaded repeatedly, but also it is not deleted automatically, meaning that if you have deleted or removed any of the files or application data from your project and you re-downloaded the entire project to your GOC, it will not be removed on the GOC's memory. So this can easily cause the memory, the 64 megabytes of the flash memory to fill up and cause a disk full error. So the user needs to pay careful attention to remove these the data, application data. To remove the unused application data, you can go to, in your engineering software, you can go to online and reset origin. Your PLC needs to be in stop mode for this. This will also delete your application program code, so it's most useful doing this once you start or try and download a new project to your GOC. There is another way of deleting individual application data files by going online in your engineering software, aka Codesys, and selecting the specific application data that you want to be removed. For this, you also need to be online with your GOC. The source code is your entire or is your entire project. So it contains all your project files. This includes your POUs, your program comments, passwords, visualization screens, libraries, and system files. When downloaded to the GOC, your source code is retrievable, as opposed to the application program code that was not, or in other words, the boot project that is not retrievable. However, this source code is not downloaded automatically to the GOC. Therefore, if you lose your program on a PC or your project on the PC, you aren't able to retrieve it from the GOC unless you have downloaded the source code to the GOC. So you are able to download the source code to your GOC manually by following the path in Codesys. So if you go to online and say source code download to connected device, you will be able to download the source code to your GOC. You can only do this while in online monitoring mode. You can also upload from the GOC to your PC the source code by going to File and then Source Upload. So something to note when downloading or uploading to and from the GOC, you can password protect this action to protect your code. And this action also does not stop the normal operation of your GOC. So while uploading or downloading your source code, the operation of these screens as well as the PLC logic continues as normal. So lastly, we go to the FRAM. So as mentioned previously, our FRAM stores the retentive variables as well as setting data. So setting data just refers to the IP settings or some of the screen settings. And the retentive memory we will be discussing quickly here. So any variables that you declare as retentive is stored in this memory. This means that variables maintain their values during a power cycle or warm start. So when mentioning a warm start, this is any power off that does not include writing your program to the GOC. So on a cold start, your retained variables are reset to 0 or the user-defined value, with a cold start being when you have uploaded or updated your program, downloaded or updated your program on the GOC. So the GOC allows for 4 kilobytes of memory to be retained, 3 kilobytes of this memory being in the data memory, and 1 kilobyte being in the marker memory. To declare a variable retentive, you need to use the keyword var retain to define a variable as retentive. So this would happen in either your local or global variables window, an example of which you can see on the screen right here. So you can see the keyword var retain is used, and then the first variable declared is declared in the marker memory retentive range, and the second is just a variable in the data memory. So important thing to note, for the marker memory to be retentive, you need to both declare it using the keyword retain as well as declare it in the range of the retentive memory, so that range we mentioned previously. So declaring a marker memory outside of the range, even though you use retain, will mean that it won't retain. Similarly, if you don't use the keywords for retain, but use the range for the retentive memory, it will also not retain. So you need to have both var retain as well as the range correct. So for example, for this one, the keyword var retain was not used, although the range, it does fall in the retentive range. This variable will not be retained. Another thing is that your function blocks instances can be declared retentive. So you would also use var retain and just declare the instance name. Doing this will have all the data of the function block also be retained. So next we will be moving to addressing. So as mentioned previously, the GOC43 is programmed using the code assist software. As such, the memory of the GOC is assigned bytewise. And all this means is that the size of a register, so is 8 bits. So register 0 has 8 bits, the next 8 bits is register 1, and so forth. This is generally opposed to what you have in the standard MALSEC PLC ranges, which are typically addressed word-wise, so every 16 bits forms a word register. Our format for our addresses is quite specific, and it forms something of the sort as you see on the screen. The percentage sign is just indicative of it being a fixed memory, as opposed to what you would have for your data memory, which is not fixed. The next letter indicates the memory type. So for here we have a M, which would indicate marker memory, an Q would indicate output memory, and an I would indicate input memory. As you can see, there is no option for data memory because, as we've discussed, it does not have any addressing. The next letter indicates the data type. So whether it's a Boolean, a byte, a word, or a double word, you'd either have an X, B, W, or D, in which case here we have a Boolean or a bit. The next would be your memory address or your memory your number, for which the ranges for your input and output are as follows: 0 to 31, 32 to 2047. So that would be your main unit and extensions and your communication protocols. Same with the output, main unit and extension and your communication protocols. And with your marker memory, you don't have that subdivision, so you just have the 0 to 32,767. Now, if you want to use or reference or address a word, this is where you would stop. But if you want to address or reference a bit, you would use a decimal point to address a bit within your byte memory, with the last number being the byte position within, bit position within the byte. In any of your memory types, you can reference a bit, byte, word, or double word using the format we just discussed. However, you need to keep in mind that in this memory, data type addresses aren't independent of one another, they overlap, meaning that bits and bytes can be referenced within the same register number. So for example, we're going to be using marker memory, and I'm going to be showing you some examples just how you would address memory. So for the first example, we'll be addressing a bit. So if we take bit 1 of register 1, the addressing will be as follows: percentage sign MX 1.1. So for another bit example, in register number 2, bit 3, the address will look as follows. But now if I want to go address it according to byte, you'd be using percentage sign MB0 for the first one. So the byte addressing is relatively straightforward because it coincides with how the memory is already arranged. So as you see, every 8 bits has a number. So the complexity of this comes when we go to word addressing, because words are 16 bits, so it takes up 2 register numbers as follows. So if you see here, we have register or marker memory word 0, which takes up register number 0 as well as register number 1. Now, if we want to go and declare another word register, doing so with using 1 would mean it overlaps with word 0. So if you want to declare 2 consecutive word variables without it overlapping, you'd have to move over to marker word 2. The same applies to double words, which is 32 bits. So that would mean 4 registers are being used. So that would mean if I use percentage sign MD0, which is marker memory double word 0, it would use registers 0 to 3. Now declaring MD1 would overlap in register number 1, 2, and 3. So having to declare the next consecutive one without it overlapping would mean you'd have to go use percentage sign MD4. As you can see, you can choose to reference a bit, a byte, a word, and a double word, which all can overlap with one another. Something important to note as well, when addressing or referencing a word, the byte with the smaller number will always be the lower order byte. For example, if you want to use percentage sign MW0, byte 0 would be the lower order byte, and byte 1 would be the higher order byte. Same principle applies when you use or reference a double word, with the byte significance, the byte significance increasing with your byte numbers. So for percentage sign MD0, you would start off with byte 0, 1, 2, and then finally 3. So that is all for the addressing for today. Our next section is the I/O mapping. So for the IO mapping, we'll largely be focusing on how the inputs and outputs of the GOC is mapped to what addresses they are mapped. So as we have discussed, the input and outputs are mapped to %I and %Q. A summary of the ranges for each for the main unit, as well as the extensions and the communication protocols, is as follows. Just a note here, the range of byte 0 to input, byte 0 3 to 11 for both your input and output is reserved. So it does not have a function, but it's not usable memory. Furthermore, the main unit input and output reserves byte 0 to 1 for input and output, byte 2 for input and output for your LED keys and quick access keys, byte 12 to 13 for input and output for your IO extension slot 1. For your second slot, it's byte 14 to 15 for both your inputs and outputs. And for your communication protocol interface, it is byte 32 to 2047 for both your inputs and outputs. When it comes to your built-in digital IO, the ranges for your inputs are input word 0, or if you want to go to the bytes, input byte 0 to input byte 1. Your outputs are the same, it goes to output word 0. So for the digital IO, whether your main base has 8 inputs and outputs or 16 inputs and outputs, 16 or entire word or 16 bits is reserved irrespective of whether what option you have for your inputs and outputs. So as you can see on the side, each of your digital IO is given a symbolic name by default. So the default name is D_DI_main and underscore its number. The user can replace this default symbolic name with a custom one. For instance, I replace the digital input 1 or digital input 0 with F_I_start BB. You can do this for all of your digital inputs as well as your digital outputs. The built-in LED keys occupies input bits in the register 2, so input bits 0 to 3 of register 2, and also occupies the output byte 2. The input bits of the LED keys are used to indicate whether the user has pressed it. So it turns on when pressed, when the button is pressed. As for the output bytes, these are assigned to the color green and red. So each key has an output byte for green and an output byte for red. When the green one is pressed, or when the green one bit is turned on, the LED lights up as green, and when the red one turns on, the LED lights up as red. When both of these bits, output bits, are turned on simultaneously, the LED key will light up yellow. And similarly to the digital input of digital IO in general, you can rename these LED inputs and output bits, or you can just keep the default symbolic name that is already there. The quick access keys only have input bits assigned to them, which is input bit 2.4 or of registers 2 from bit 4 to 7. As you can see, this occupies the same input byte as does the LED keys. Each of the input bits are also assigned to turn on when the button is pressed. As you can see, there are no output bytes because there's no LED key or output function assigned to them. And they also have their symbolic name, which in this case would be underscore key underscore F1 or F2 or F3 or F4. You can also replace this default symbolic name with a custom one. When it comes to your IO extensions, each slot has its own range for its inputs and outputs, with slot 1 having input word 12, slot 2 having input word 14, slot 1 having output word 12, and slot 2 having output word 14. So the functions of your extensions that is installed or plugged in on your GOC varies, meaning that the IO in this range being used will also vary. When it comes to your analog IO extensions, the input and output IO assigned to the extension slot is used as a control word or status word, with your control word being used for enabling channels and your status word being used for statuses, whether your channels are healthy or whether the extension is in fault. An example of which you can see in this screenshot right here. So our status word, it checks whether the channels are healthy or not, and it also has a bit for whether the extension is in fault, and the channel enable bits are in the control word. This range or any of these ranges is here do not account for your channel or your analog input or output values, as these are found within your IEC objects, which you'd be able to see in this screenshot. When it comes to your digital IO extensions, these are mapped to the available IO points, which makes sense. So for example, when we have an 8 input extension module, which is this GC-8EX-ES module, the bits will be assigned to 14, register 14.0 to bit 7 of that same register. You can see the screenshot here as well. Apologies. So any of the IO not used in any of these examples, whether it's an analog or digital extension module, that IO becomes redundant. Thus meaning when you're not using the IO due to the fact that you don't have any extensions on your GOC, or the module plugged in does not use all of the mem of IO available, these IO points are still reserved by the main unit or the extension unit and cannot be used elsewhere in the program. For your communication protocol interface, the IO ranges are input byte 32 to input byte 2047, and the same with the output, same range, just in the output memory. The communication protocols to which this applies are your Modbus serial protocol as well as your Modbus TCP. So the third protocol that the GOC has is CC-Link I-Field Basic. However, this doesn't use this addressing range because the user defines memory or addresses in the marker memory for the link IO of the CC-Link I-Field Basic protocol. Therefore, this range only applies to your Modbus protocols. This also means that you have 1008 input words as well as 1008 output words available for your Modbus protocols. As you configure your GOC for the different protocols, or whether you configure it as masters or slaves, the memory or the addresses are automatically assigned. So for example, setting up your GOC as a master, for each slave connection you set up, the addressing will be assigned automatically per the communication instruction. So that is per whether you are reading holding registers and how many registers you are reading or writing. This applies for both your Modbus serial as well as Modbus TCP. You are also able to assign symbolic names to these registers being read and written via communication protocol. These do not have default names, but you can also not simultaneously give names to a word register or as well as the bits within them. This will make sense in the next slide, which is here. So this is an example of what I just explained. Here I have the GOC as a Modbus TCP master, and I have configured a slave to read holding registers as well. Well, read a single holding register as well as write two holding registers. As you can see, the reading is assigned to input words or an input word, and the writing is assigned to two output words. So that is due to the fact that I configured it to write two holding registers and only read one holding register. Here you can also see I have given a symbolic name to input word 32 that is read holding register. So alternatively, you can also name or give a symbolic name to each of the individual bits, which you can see in the output section here, but you cannot do both of these simultaneously, as you will get an error. So when adding a second slave to this configuration, it will also keep on or automatically assign the addressing according to what has already been assigned. So for instance, if I now go back to slave 1 and add more holding registers to read, it will follow on this range that you see here already. When it comes to setting up your GOC as a Modbus slave, the IO is also automatically assigned, but the big difference between setting up your your GOC as Modbus slave versus master is that the mod slave configuration automatically assigns 10 input words and 10 output words, whereas setting it up as a master, it assigns addressing according to the communication that you are setting up. You are also able to assign symbolic names to the input words as well as the output words when your GOC is set up as a Modbus slave. So next we are going to be discussing the IEC objects, which are essentially variables that are predefined by the by Mitsubishi Electric, and they don't have addresses. They are assigned or have predefined symbolic names. In your IEC object variables, these include your built-in analog variables, high-speed counter variables, alarming variables, data logging variables, as well as your system variables. So for the features of the GOC, which includes your analogs as well as your high-speed counters and your alarming and data logging, these variables store values and statuses associated with these features. Whereas the system variables are IEC objects that are used to exchange information between the CPU and the application program, and is mainly used for checking up on the statuses of certain parts of your GOC, as well as you can use it for diagnostics. An example of which, or sorry, the variables of the system variables start with the prefix underscore sysvar followed by a unique name after the prefix, which indicates to its functionality. So most of the information that the system variables hold can be found on the system menu on the GOC itself, but you can also access it through your program using these variables. A list of the system variables is for your is the CPU, disk memory, Ethernet, HMI, memory pointer, your RTC, SD card, and version info. So as you can see, each of them have specific functionalities. Now, another thing you might notice is that the description for system var CPU gives CPU status and diagnostics variables. This is because each system variable is not a single variable, but rather a group of related variables categorized together, all with a similar purpose. There's a detailed breakdown of all of these variables within these groups in the GOC's manual, but I will just give a small example. So for your system var CPU, you have 14 variables, all of different types. So it can be a D-word arrays of string, etc., etc. So if you want to access a single variable within this variable group, you use a dot operator. So an example of which is right here. So underscore sysvar CPU, use the dot operator, then refer to your specific variable within that variable group, which is system bits. And because the system bits, each bit has a separate function, I use the dot operator again and indicate that I want to use bit 0, which is always on. So that's similar to your SM400 in the newer MALSEC PLC range. So if you want to use always on, you'd refer to this system variable. If you aren't referencing a bit within this variable, you'd just end off with the variable name. So for example, sys for CPU dot ww or w warm start counter. So as you can see, I'm not referencing a single bit within this. So just to give you a small view, this is the list of system variables as was in the presentation as well. And there is a detailed breakdown. So we went to system bits, and bit 0 remains always on. So as you can see, each of these bits have a different function. There's a long list detailing the function of each of the variables within every single group of system variable. And that is all for today's technical session. I hope everything was clear. The next technical session for the GOC is on the 2nd of July and will be covering the PLC programming within the Pegasus environment.